Good morning, everyone. I figure let's get started. First, with the announcements as usual. As I mentioned in an announcement on Canvas, first off, nice work on exam 2. For one, the scores were overall just a lot better. So nice job. And I want to ask about that in a moment. But also on written homework and labs, those scores have generally been improving. So whatever adjustments you're making, nice work there. And actually, as far as exam 2 goes, I wanted to ask, so if you wouldn't mind maybe sharing in chat, and again, I'm the only one that's going to see it. I just said it, so host only. If you want to share in chat, why do you think you personally did better, or if you didn't do better, did you just change anything as far as the first exam? In particular, if you did much better, do you think it was extra time that helped? Do you think the fact that it was cumulative, so you've seen part of the material before? Did you take a new study strategy? Were there some other reasons? So if you wouldn't mind sharing just in chat so that only I see, why do you think you did better on this exam than the first one? I'm just kind of curious. That'll help me try to make sure people are a little more successful next time as well. So yeah, do you think it was extra time? Do you think it was cumulative? So you've seen material before. Did you try a new study strategy? Was there just something else maybe I'm not aware of? Yeah, anything you feel comfortable sharing, I'm very appreciative to see, because it'll help me just structure things in the future so that we can have good exams, hopefully for 3 and 4. Okay, yeah, I'm getting a lot of stuff in chat here, so I appreciate that. I'll look back over that stuff later more carefully, but thank you for sharing what you've shared so far. Appreciate it. With that said, and feel free to keep sharing as I'm talking here. I'll certainly go over the chat more carefully after the session is over today. But I want to remind you, of course, exam 3 will be cumulative. So will exam 4. They'll just keep building on each other. And then at the same time, you would have just turned in lab 4 and written homework 4. So now looking at lab 5, written homework 5, those are also accessible. I kind of intended them to be more focused on material that we've seen towards the beginning of the course, these labs and written homeworks, in particular the labs, so that we're kind of continually reinforcing that material that we saw earlier, and just to maybe make it a little more manageable. So those are certainly things you can tackle right now or whenever you get the chance for lab 5 and written homework 5. All right, that's it for announcements. I wanted to open up to any questions that you had in particular. I'm going to flip back to this page. The idea today is to look at Laplace transforms and things related to it. And that will be the theme of this 2 weeks. So the first 2 weeks was first order methods, and we saw a variety of those methods. And I think and had planned for that to be sort of the hardest. And then the second 2 week was higher order methods, where we look at mainly characteristic polynomial. And then we're looking at Laplace transform, and it's 2 weeks kind of dedicated to a particular method. And then the last 2 weeks will be power series and a little bit of linear systems as well. And actually, I think we'll touch on linear systems briefly here, but Laplace transform will be the big theme. But before that, I want to open up any questions you want to ask really quick. Okay, I'm not seeing any questions jump out, so let's go ahead and start looking at the Laplace transform. And if you're coming in after I said it, good morning to everyone. So what is the Laplace cycle? The Laplace cycle is this. We're going to be looking at 2 different spaces. We're going to have actually, let me draw this a little bit thicker to really emphasize. We're going to have a T space and then an S space. And keeping this in mind will actually be kind of ridiculously helpful. So hopefully it's a relatively simple diagram that helps you frame what we're going to be doing during this 2 weeks. Now say, and actually let me label this quick. We've got the T space, and then we have the S space. Now, what do I mean by T space? I mean over here on the left, we have essentially functions of T. That's what I mean when I say T space. And then in the S space, likewise, we have functions of S. And just in case maybe that's a little abstract at 8 in the morning, T space functions are just simply things like cosine of 3t, or let's say 4t over t squared plus 1, or something like that. I really just mean functions of t. And then functions of s, similarly, let's say 3s over s squared plus 9, or e to the s, or maybe e to the, maybe just e to the s, things like this. Let's say we have a just general function of t, we'll call it f of t. And now I'm going to erase these examples just to clean this diagram up because I don't want it to be too cluttered. But when we're looking at the t space, it is just functions of t like I've written here. And then when we're looking at the s space, it is just functions of s like I've written. Now, starting with some general just f of t, we're going to then take and map that to a function of s. And in general, we'll use lowercase f to mean that we're in the t space when we're talking about Laplace transform type stuff. And then we'll use uppercase f to mean that we're in the s space in general. Now, what we'll be doing is we will be converting from f of t to f of s, and we'll be doing that using the Laplace transform, which is kind of the script L here. So this thing right here is the Laplace transform. Now, once we've converted from a function of t to a function of s, the point of doing that to solve differential equations, because that's what we're concerned about, is we'll then take that function of s, and while we're in the s space, we'll do a conversion to, let's say, some other function, perhaps called g of s. And there, what we'll be doing is really just algebraic manipulation. That is, rewriting it. After we've done the rewriting, we'll use the inverse Laplace transform to move back from the S space to the T space, with the idea being that this G of T will somehow be our solution. So we start with an F of T, or maybe a Lx F of T. But in general, this is going to be our differential equation that we start with. We do the conversion from the differential equation to some function of s here, do some algebraic manipulation, which is just rewriting it. And then after that, we'll, and I didn't denote it, but we'll take the inverse Laplace transform. So this is what I mean by the Laplace cycle. Start out here, f of t, or a differential equation in terms of t. Use Laplace transform to convert it here. We rewrite it, and then we use the inverse Laplace transform to convert back. Now, I haven't said exactly what the Laplace transform is, so let's go ahead and look at what it is. Keep in mind, what we're trying to do with Laplace transform is convert function of t to function of s. Here's how we do it. So we define the Laplace transform, which I'll highlight here. We define this, the Laplace transform of, let's say, some function f, where f should at least be defined from the non-negative real numbers to the real numbers. We denote it like this, Laplace of f, or capital F of s. It means the same thing. We denote it as this integral. Now, I've highlighted s here. And if you think about what's going on, here we have an integral. It's improper because we have one limit being infinity, but if we don't worry about that for a second and we just keep in mind there is some limits here. When we integrate, we're going to integrate with respect to t. Then we're going to substitute in the limits. We're going to have to deal with the infinity, but there's going to be some sort of substitution. Everywhere there's a t, we should substitute these limits of integration. That's going to leave us with an s. So we can imagine, because of the limits of integration, everything with a t is going to be involved in a limit or be substituted for a constant, and we're going to be left with this s. This is the way we convert from a function of t to s, which we, I think, need to see a specific example to really appreciate. But if you can kind of keep in mind you're integrating with respect to t, the limits of integration will fill in the t, so to speak, and it will leave you with just s. And just to be really clear, when we say the Laplace transform of f, we mean exactly this integral. And while we're doing the integration, as I noted, we're integrating with respect to t. So the s can be thought of as just a constant. And I think here we'll just let it be greater than 0. Now, as I said, this may need a specific example to really sink in. I mean, at least it did for me. In fact, several examples. So let's go ahead and look at it. Say we have the function that's just t. F of t is equal to t, and we'll take t to be greater than or equal to 0. Of course, it's defined for more than that, but we want at least that. If we take the Laplace transform of t, by definition, what that is the following. We take exactly this integral whenever we do the Laplace transform, and the only thing that changes is what we put in the integrand as far as this function. The function is t, so we just put t there. I won't compute this integral, but just to compare, if we had, let's say, Laplace transform of cosine of 2t, that would be equal to the integral of cosine 2t e to the negative st dt. When you're computing the Laplace transform, everything is the same in the integral except for this function. And again, I won't compute this right now, but just so you can kind of see, this function is just placed here, but all the other framework is the same. All right, so let's go ahead and actually compute this one, Laplace transform of t. And someone asked, it's true, the limits of the integration never change. It's always 0 to infinity, no matter what. So yeah, it's a good question to ask. So these limits are always, always, always 0 to infinity. Okay, let's delete this one for the moment, just to clear that out. All right, at this point, a reminder, we want to think of s as being constant while we integrate. So think of s greater than 0, and namely s is a constant while integrating. We're integrating with respect to t, so it doesn't recognize s, so to speak. It essentially ignores it and just leaves it as a constant. Okay, so this was just t e to the negative 5t or something instead of s, just some constant. What we would do in this case is use whatever integration technique that we could think of. And in this case, I think we want to use integration by parts. And someone asked another good question. Do we think of t later as a constant when we're converting back? Is there kind of symmetry where we think of s constant one way and then t constant the other way? In fact, what we'll find is, and I'm going to flip back, we'll find that when we do the inverse Laplace transform, we won't need to do any computation using integral. So here we think of s as a constant to do this conversion as we're in the process of doing. But when we do the inverse Laplace transform, we won't have to compute it via an integral. So we won't need to do something like thinking of t as being constant in that case. So there, we don't need to worry about that type of symmetry. Once we do the inverse Laplace transform, it'll actually be, in some ways, relatively straightforward. We essentially just need to know what the Laplace transform of different things are. And then there's linearity property that we'll talk about today that we use, but there's no integral we'll have to do here. Just an integral we have to do here. And maybe it's even worth kind of stressing that here's the integration, but there's no integration that we have to do down here with this inverse Laplace. And we'll actually find that most of the time we don't even have to do the integration, but we want to see how it works. And sometimes we'll be asked to do it. We'll need to do it. But a lot of times we'll actually be able to use something called a Laplace table. But sometimes we absolutely need this integral, and it's good to just see how this works. So let's go ahead and do it. As I mentioned, let's use integration by parts. If we do integration by parts, we need something to be u, which I'm going to pick to be t. Then du will be equal to dt. Then I'll say dv is equal to e to the negative st dt. And then v, if you're thinking of s as constant, we should have negative 1 over s e to the negative st. Now let's substitute these appropriately. And we will get uv, which is negative t over s, e to the negative st. That's u times v. So let me just remind us, uv minus the integral of v du. And now, since we have limits of integration, we'll want to post those here, going from 0 to infinity. And then minus the integral v du. V is negative 1 over s, e to the negative st. Du is dt, still going from 0 to infinity. And then we can now do the last integral, and then I think we can tackle how do we handle all these infinite limits. That's very probably something that several of us forgot because it's kind of been a while since we've had to actually do an integral with the infinity in the limit. So let's see, this is going to be one more time, negative 1 over s. All right, here we are with this expression. I'm going to take this and put it onto a new page. And if you've got any questions from this page, how I came up with this, you're certainly welcome to ask. It's been probably a minute since we've done integration like this. So if you're curious, feel free to ask. I'm going to put this on a new page though. So what we've said so far is the Laplace of t is equal to this expression. And I'm going to jump back and grab this heading. keep track of where we're at. All right. And let me just clean this up a little bit, just for the sake of computation. I'm gonna do a few things to clean this up and hopefully simplify it. And if you're at all curious why this is so, just let me know. But I'm gonna notice I can factor out a negative 1 over s from both terms, leaving, actually, and we've also got an e to the negative s we can factor out, though that we'll still have to evaluate. And I guess that's going to be t, actually. And this should be, actually, let's do e to the negative st, leaving us with t. And then over here, what are we left with? Plus 1 over s, I guess. No, I'm going to want to do that separate. Okay, clean that up a little bit there. And now I'm going to say that since we have this infinite limit here, whenever we encounter an improper integral, what we'll want to do is switch to doing a limit. So that's how we handle improper integration. We switch to a limit. So now what I'm going to do is say that this is equal to, since negative 1 over s won't have anything to do with t, I can write the limit starting after that. I'm going to say the limit as b, now let's really stress it, the limit as b goes to infinity of all this, which I'll just copy. This is, again, if you remember back from Calc 2, I guess, this is how we handle infinite limits and integration. So we basically switch from saying infinity here, which is not a real number, so we can't just quote unquote plug it in. That won't work for infinity. You can only plug in real numbers. So here we're going to switch and say let b be a real number that isn't infinity, because infinity isn't one. We're just going to let it go to infinity. That's the workaround here, how we actually compute these things. Now, a little bit more rewriting. And after you've done a few of these, they're actually not too bad, but if it's been a minute, it may seem like a lot. But a few of them, and it's all comes back. Now let's substitute in both b, which we can think of as a real number, and 0. First, we'll do b. So we're going to have b, and then I'm going to rewrite this just so I don't have to do another step of rewriting. We're going to have e to the s times b. And you could have used something else in place of b. I don't know why. That's just how I learned it. And then we're going to have plus 1 over s. Let's see. E times 1 over e to the s b again. And that's just the first part. Then we're going to subtract from that 0 times e to the s times 0 minus 1 over s 1 over e to the s times 0. Okay, here we are. If you guys are okay with it, I'm then going to actually erase this step just so I can move all this up. Okay, there we go. Now at this point, we want to figure out what these values are. Some are obvious. This is clearly 0 here. It's 0 over 1. This we know is just negative 1 over s. Now the question, what are these things? Now remind us that we said s was going to be equal to, or s is going to be some constant, or we'll think of it like some constant, and in particular, s is greater than 0. If we look at that here, just in chat, so I know you guys are following, or I know you're not, either way, just so I know. What do you think this second term is going to be in total? Either this thing or, the whole thing, either way. So at least just this limit or this limit times this value. What do you think this is going to be? You just want to say in chat so I can get a feel for how you guys are following it or maybe having trouble. All right, so thank you for the answers. Those of you who put something in chat, appreciate it. Think of it like this. So for a moment, 1 over s, that's just some constant. For this thing, all right, well, what's that going to be? Well, nothing changes in the limit with 1. And this thing, as b gets bigger and bigger and bigger, so if I wasn't clear, I mean, as you take the limit, as b gets bigger and bigger and bigger, what you're going to have is s times b is going to get larger and larger and larger. Since s is a positive number, if you take s, a positive number, times b, which is going to positive infinity, so b is eventually positive, it doesn't even start there. So it gets larger and larger and larger and larger and larger, and you're taking e to an increasingly larger number, which means this thing is going to grow without bound, and it's the only thing that's growing and changing, and it just always gets larger forever and unboundedly. It's not like it just gets larger and approaches some finite number. It's unbounded, so it's bigger and goes off to infinity here because b does. Therefore, you're going to have 1 over something that gets larger forever, goes to infinity, and then you'll get 0 here. And then the limit is 0 times 1 over s, you're going to get also 0. Now, it may not be so clear what you do here, because while exactly the same thing happens, that you have e to the sb and e to an increasingly larger exponent, you also have the numerator getting larger at the same time. So your numerator goes off to infinity positively, and the denominator goes off to positive infinity. So now the question is, well, which one wins? Because it's kind of like infinity over infinity. But, and as actually someone pointed out in chat just here, so it's a good thing to note, and they said it well, so I'll basically paraphrase them. Someone said, oh, well, this actually goes to 0 too, because when you're taking b to infinity, this thing grows way faster than this, and that's exactly the right way to say it. So, yeah, shout out to the student who said that. This will definitely be 0 because exponential grows so much faster than this one. So it's kind of a battle that if you had, let's say, e to the sb, where b was in the numerator, then you had b down here. This thing, this would go to infinity as b went to infinity. The reason being is this exponential grows much faster and it sort of overpowers this b here. So it outpaces, if you will. But then in this other case that we have the reverse, that this b doesn't grow nearly as fast as this one does. So it sort of outpaces it and outpaces it such that you get 0. Therefore, the only thing we end up with that is not 0 once we take the limit, and just to be clear, these are all things we get from the limit. So maybe I'll color this kind of cyan here to say that's the limit. then we get negative 1 over s times negative 1 over s. And now, in total, we got 1 over s squared. So the Laplace transform of t we went through, hopefully slowly to bring back some memories, or slow enough that at least jog some memories of Calc 2. What we ended up with going through this process is 1 over s squared. Now let me jump to the next page. I wanted to see what I put next. Yeah, okay, perfect. Now you can do this with all sorts of functions. You can just sit down and you can compute what is Laplace transform of blah, what is Laplace transform of this other thing, and so on. And you just compute all these out. We did one. We saw that the Laplace transform of t is 1 over s squared. Okay, well, what's the Laplace transform of 1? What's the Laplace transform of cosine of alpha t? What's the Laplace transform of an exponential, and so on. So you can go through all this stuff, and someone has, well, many people have it at various points, and they've computed all sorts of different Laplace transforms. What we'll mostly use, just because it does take a while to actually do this, and we're not so focused on making sure that you can just at any moment compute the Laplace transform completely through like this for any given function. It's true, we'll want you to be able to do that for some simple functions like t, or like a exponential and so on. But the main thing is being able to use the Laplace transform to compute uh, differential equation solutions. So certainly familiarize yourself with this. Make sure you can go through one like this, or try it in a simple case. Like I think 1 and the exponential are both very good. But for the majority of time, what we'll be using is this Laplace transform table. So if we jump to this table here, and you can just Google Laplace transform table and find a variety of ones. This is one that I had, at least in I think it was a Stewart calculus book. And to me, it's kind of the best, because it has everything you want and is organized, I think, nicely. But maybe you'll find another one you like more. But we see there's a table here, for example, and I'm going to zoom in a little bit. Hopefully that doesn't give terrible resolution. Okay, that's kind of bad, but we just need it for a second. And actually, can you all see this kind of? Like, I think the resolution's not great, but can you see what I'm highlighting here roughly? Okay, cool. Yeah, of course, you'll be able to have your own with higher resolution. I had to shrink this down. I think that's why it's so bad to fit it on this page. But yeah, where do you find this thing? Google it. Just Laplace transform table. Someone asked, is it on Canvas? I don't think so. I can post it on Canvas, though, if you want the specific one. But just a Google of Laplace transform table will get you this. So how this thing works is, let me zoom back in here. If you look at this case, and again, sorry for the bad resolution, but suppose we look at the example we just did. So we did t, Laplace transform of t. That would, in this case, if you can tell that it's t to the n, if n is then 1, we get n factorial over s n plus 1. So let n be 1. 1 factorial is 1. And then s to the n plus 1, since n is 1, that's s squared. So we have 1 over s squared, which is exactly what we computed. And you'll find that if you did it for a general t to the n, that you could come up with this formula. I'm sure everyone could do it. I think it would just require doing integration by parts however many times n is. So if n is 3, you'd have to do integration by parts 3 times, which is cumbersome, but you can kind of find a pattern there. Point being is, here's what it is. I recommend, if you want to get the practice, doing this one on your own, Laplace transform of 1. It's kind of a simpler version of the one we just looked at. And then also, I'd recommend doing this one. This one I think almost might even be easier. So the exponential and just 1 are both good classic integrals to do, and you really get the idea after doing them. But once we have this table, what we're going to do is we're just going to use it to find Laplace transforms. So for instance, if I want to know the Laplace transform of 1, what I would do is I would consult the table, and maybe let me color this. I think you guys probably get what's going on, but just to be really clear, if we look at the, let's make that a little more noticeable. Yeah, there we go. If we look at the Laplace transform table, what we find is that the Laplace transform of 1 is simply 1 over s. And that's all there is to it. Let's say we want to find the Laplace transform of sine 3t. Okay, let's color that perhaps green. And then let me switch to green. We find that in the table, and this is going to be a silly thing, but can you guys just point out in the table like which number it is, if you can see if the resolution is decently enough? Do you see which number it corresponds to? Let me zoom in, maybe that'll help. So where would I find sine of something times t? And again, it's a simple thing, but I just mean it to be give you a little practice working with this. Okay, good. For those of you who put something in chat, I appreciate it. Indeed, I guess, I don't know if it's line 7, but part 7 at least is exactly what we want. So we take this and we say, there we go. That's going to tell us that if 3 is our A in that case, we're going to have 3 over s squared plus 3 squared, which of course is 9, but I'll leave 3 squared just to really emphasize the point. And so on and so forth. If we did the exponential, we would get, let's see, what line is that? I think that's line 2. And that's going to be 1 over s minus negative 8, so s plus 8. And then finally, I'll do this last one. And that will be, which line? Let's see. E to something times cosine. Which line is that here? 20, I think. A little hard to see on the white background, but I think we get the idea at least. So we have s minus 2 divided by s minus 2 squared plus 2 squared, which is 4. So this is consulting the table. And someone asked, is it easier to work things out or use the table? Well, definitely using the table is the easiest. But as I mentioned, you'll definitely want to be able to use the integral. And what I would really recommend to make sure you've got that down is doing these two. Do Laplace transform of 1, just show it is 1 over s, and then Laplace transform of e to some a times t. Doing those two will really give you the idea of how this works. Oh, and someone pointed out, yep, it would be plus 16. Thank you. I was looking at the 2 and squaring it. So thank you for catching that, the plus 16. Okay, so now the question is, this is fine. If we're taking the Laplace transform of 1 and we've got access to the table, or Laplace transform sine 3t, we can just consult the table and there we go. We know what it is. All right. Well, I'm going to flip to a new page. What happens if we get, let's say, Laplace transform of 5? Now, okay, keeping in mind Laplace transform of 5, I'm going to flip back. Laplace transform of 5. and I'll put question mark. If you consult the table, there's not going to be anything that really jumps out at you as far as what is Laplace of 5. We have 1, but we don't have 5. We have things with exponential and t's and sines and cosines and all this sort of stuff. But nowhere do we see like just 5. You could maybe finagle it from some of these more complicated formulas, but there's actually a way easier way that we can find what is Laplace of 5. And we'll do it using Laplace of 1, but we need another property. That property is called linearity. The Laplace transform and the inverse Laplace transform both have linearity, and here's what that means. So linearity says for all, let's say alpha, beta, that are real numbers, we can take the Laplace transform and let's see, how do I want to write this? Let's actually maybe start this in white. Let's use colors for these constants to highlight what we're doing. Okay. So say what we have is an alpha and beta, they're real numbers, and we're taking alpha times f of t plus beta times g of t. And we should say we have two functions in the quote unquote t space. How we can write this linear combination alpha times ft plus beta times gt, we can write it as alpha times the Laplace transform of f of t. And there's essentially two things happening here at once. Then we'll add to it beta Laplace transform of g of t. All right, now just to try to grapple with what we did here, would you write in chat what happened going from the left side of the equality to the right side? So as we went from here over to here, just as you see it, and I'm not looking for anything too complicated. I'm just looking for you to kind of process what we did. And there are two particular things, but if you can only see one, that's okay. Just what do you observe as we go from the left side to the right side? Just in a basic sense, what did we do? Okay, I'm seeing some good answers here. Yeah, and if you misspell things or whatever because you got something else going on, that's okay. All right, yeah, you guys are seeing it, the two properties. And I don't mean it for it to be very complicated or anything, but it's simply we're splitting it across addition. So we go from having a single Laplace transform to taking two Laplace transforms and adding them up. And at the same time, we can factor out these constants. So there's kind of two parts. There's Laplace of f of t plus g of t is equal to Laplace of f of t plus Laplace g of t. I usually say this as separating it across addition. So instead of doing a Laplace of a sum, we do a sum of Laplace. And then the second thing is that if we have a constant, say Laplace of alpha times f of t, we can factor out that constant and get Laplace f of t times alpha. So two different things. Factor across addition, if you will, or split across addition, and then factor out constants. That will allow us to compute, let's say, the Laplace transform of 5. How do you do that? Okay, well, let me jump to a new page. We're going to use linearity. Laplace transform of 5 we can alternatively say that's the Laplace transform of 5 times, which I'll put in this magenta to remind you of the alpha, or to make you think of the alpha that we just looked at. This is like 5 times 1. And now we can factor out this 5 because Laplace transform is linear, leaving us with 5 times the Laplace transform of 1. And now we know what that is. That is the Laplace transform of 1. We just saw a little while ago that that is equal to 1 over s. Now, in the same way, actually, let me give this some more room. In the same way, we've got now, let's say, negative 3 cosine 2t. I'll let that be colored magenta. I'll let this be colored green. In the same way, we've got, let's say, cosine of 2t being our f of t, sine of 7t being our g of t, if we are to use the same format that we just saw. And now we can, one, factor it across addition. And I'm going to do it in 2 steps, but you can, if you like, do it all in 1 step if you feel comfortable. And now, if you like, you can use the factoring out of constants. Or again, we could have done this all in one go, but just to make really clear that we're using 2 different properties. And then at this point, I've claimed we've got it down as far as we're going to need it to be reduced down to. At this point, you can do one of 2 things. You can do the integral, or you can consult the Laplace table. Of course, the Laplace table is going to be easier as long as you can read it appropriately. But for simple functions, again, like I mentioned, it's certainly good to be able to do them. And it's very likely you'll see something like that pop up on a test, like work through this simple, Laplace transform of actually using the integral. But let's for now just say we reference the table, and supposing we had it next to us, I remember these enough that I can just write them. For cosine of 2t, that's going to end up being s over s squared plus 4, because we take this number and square it. And then in the second case, we'll have sine, which will end up being 7 over s squared plus 7 squared, which is 49. We add those together. And that's really, really all there is to it. Now, if we think about the Laplace cycle, what we've done here is that first part of the cycle. So thinking back to the Laplace cycle that we looked at in the beginning, we had the t space, we had the s space, and here we had, let's say, negative 3 cosine of 2t plus 8 sine of 7t. We took this thing, we converted via Laplace into this other thing, which is now in the S space. The rest of the cycle, once we actually get to solving differential equations, will be to algebraically manipulate and then work backwards with the inverse Laplace. So we just did this first part here, as it were. We just followed this arrow. But there'll be, 2 more arrows in the ultimate process when we go through the whole thing to solve a differential equation. So we just did the first part. Okay, let's see what's next. That's it. Okay, well, now I want to open up to questions you guys have as far as this goes. That's all I had prepared. Uh, and we can do some more examples if you like, or we can just leave it at that. So, do you have questions on this process, or did the process seem straightforward? What do you think either way? Actually, if it did seem straightforward, if you want to just say that in chat so I get a feel for the room. But if it was confusing, if you didn't understand some steps, let me know that too. So someone asked, why would we need this technique? Yeah, that's a good question to ask. What's the point? So the point is it's going to be a way to solve differential equations. So what we'll do is we'll start with a differential equation, which we haven't started with. We're just getting comfortable with just taking Laplace transforms of functions. But eventually we'll take the Laplace transform of an entire differential equation, convert it into something in the S space. Then that's where the algebraic manipulation will come in. And then we'll do the inverse Laplace transform, essentially undo it. And then that will give us a solution. So going through the whole Laplace transform cycle, the whole cycle itself is so that we can solve a differential equation. We haven't started with a differential equation here, and we haven't gone through the whole cycle. But once we actually have a differential equation to start with, we'll basically apply Laplace, do exactly what we've done here, then do our algebraic manipulation, and then go backwards with the inverse Laplace. And then kind of like magic, all of a sudden we'll have our solution. It's really impressive once you see the whole cycle. So the point is to solve differential equations.
To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.